So our first speaker today is Thore Husfeldt, and he's a professor at computer science at Lund University and IT University of Copenhagen. He's a core researcher at the Basic Algorithms Research in Copenhagen Center and the current chair of Vetenskapsrådets expert panel for computer science. He will give an introduction to algorithmic fairness, an attempt to understand and perhaps solve these issues. And with those words, I leave over to Thore. Welcome.
Good morning. Thank you very much for the very nice introduction, and thank you very much for giving this opportunity to me. I'm here in Copenhagen. I hope this works. So I will now activate the clicker and hopefully see my first slide in a moment.
For the technical team to get the slides in order. How is life in Copenhagen?
It's very much like in Sweden. I live in Sweden, so I commute over the bridge to Copenhagen almost every day.
Okay. And how is
the masks here and not there?
Perfect. Now I guess we're ready for the night. Okay.
Yeah, let's see. I want to see my own slides.
Right. So how is the Copenhagen Machine Learning Society? Okay. Now.
Oh, it's very, very
big.
Oh, there we go.
Okay.
Almost.
Okay.
So now you may be seeing my first slide. I see only half of it. Are you seeing the whole slide?
We are seeing the whole slide.
Okay. So welcome to this introduction to what I call the Fairness Six-Pack. I will try to introduce 6 different fairness notions to you. You can see all of them here, but I will reveal them bit by bit again during the rest of the presentation. This will keep us entertained to something like 9:55, I guess, and then there may be time for questions. So what this is my best attempt to explain the concept of group fairness to you. I have a brief comment to the technical people. I would really like to see my entire slide. Because it seems weird to me that I can't see the slide I'm speaking over. So if you could adjust the picture so that I'm not seeing myself, but my own slide. Almost. Okay, now I see almost my entire slide. And basically what I want to explain to you is the way that I would have hoped somebody explained this to me. So by now, I think so there's nothing new in this. It's just my honest attempt to explain something that I found fascinating maybe a year or two ago. My ambitions are to be minimal, complete, interesting, and accessible. So minimal means that I would try to keep to as few concepts as possible. So I really try to pare this down to the bare minimum. On the other hand, this tiny framework that I want to establish, I will then want to explore fully. So this is both a broad picture talk, it's a big picture talk, but it's also very, very complete in that the tiny part that I want to tell you that I will explore that fully. It's large enough to be interesting. So many of the non-trivial phenomena that appear in connection with studying fairness, in particular for groups, do appear, and I can explain them here. And I want this to be accessible. So everything is from first principles. There are very, very few assumptions about your background, and there are pretty pictures. I also assume that we have no shared moral intuitions, which is sometimes difficult when you discuss fairness because it's such a value-laden concept. Okay, so this is our setup. This was already mentioned in the very nice introduction. We have some kind of blue box, which we could call the AI, or the model, or the machine learning procedure, or the algorithm. So from an engineering perspective, that would be some kind of algorithmic process, but the talk is broad enough that we can even put other sources of mechanism design under this umbrella. For instance, this could be a law and we could be lawmakers. So X is an individual which is fed into this blue thing, and out comes one of 2 decisions, 1 or 0. And it's not important for the talk whether you view this as a mechanism to decide job applications, grant applications, whether you go to jail, whether you see an ad, whether you get a scholarship to Harvard, whether you're matched with Alice, or you receive a treatment in the medical profession, you get a loan, pay the full price for the flight, and so on. You all have seen 1,000 talks that give specific examples of this kind of binary decision where an individual is treated by, for instance, a machine learning procedure, which then has an outcome that is either 1 or 0. The outcomes may be very positive. You may get a scholarship to Harvard, or the outcome may be negative. You may be selected for security check at the airport. Again, this is not important. This is a value-neutral talk. Okay, so taking a step back, above is the process we want to study and maybe improve or modify, at least understand. And I introduced 3 different variables, G, S, and T, and they are all on the slide below. So the first one, which makes there's a talk about group fairness, is that individuals are either in the green group or the red group. So G is 1, meaning you're green or Greek or belong to the group, or it is 0, which I draw as red. And think of these as Greeks and Romans. Many societies have, some of the best and some of the worst societies ever existed, have this ambition to separate population into 2 disjoint groups. Could be gender, it could be race, could be caste, could be ethnicity, could be class, and so on. Could be religion. So let's just assume there is one of these, and in order to keep this as neutral as possible, I suggest you think of them as Greeks and Romans. Greeks are green, Romans are red. So that's the G variable, it's 1 or 0. There's a selection variable, which just remembers whether you got selected by the blue algorithm at the top. So if you're inside the heavy black frame, then you have been selected. If you're outside the heavy black frame, you have not been selected. S is 0. If you want to think of selection as positive, think of selection as scholarship. If you want to think of selection as negative, think of selection as security check. All of these things start with an S. And finally, there's the target value, T. You can think as T for truth if you find that the blue box tries to determine some kind of truth. Otherwise, talent harmonizes with scholarship. So the procedure should select talents for scholarships, or it should select terrorists for security checks. So there's a positive way of understanding T, and there's a negative way of understanding T. So these are my 3 variables, G, S, and T. And this is rich enough for us to introduce many of the things that you will know by heart. If you are active in machine learning or data science, for instance, true and false positives, true and false negatives are easily depicted in this framework. And if we add the groups as in the right part of the page, then we have this quite rich but still very small framework where we, for instance, can talk about talented Romans that were selected for the scholarship at our completely fictional Athenian School for Homerian Poetry. So G can be 0, meaning that you're Roman. S can be 1, meaning that you were selected for the scholarship. And T can be 1, which means that you're actually talented at what you were selected for. Right? In that case, you are inside the bubbly, heavy black frame. You're also dark red. And all the other combinations are also on this picture except for 1. So 7 of the 8 different ways that these 3 variables can have different values are on that picture. And as far as possible, I will stick to pictures like this in order to explain these phenomena. Okay, we need 2 binary relations for math. One is the simplest one, equality, which we all know and love. So if I can say that 2 of my 3 random variables are equal, then I can, for instance, model a utility. So for instance, it would be, in many contexts, it's good for us if the selection mechanism is very close to the target value. So if S is T, then our selection mechanism is maximally useful. And gluing these 3 symbols, S, equality sign, T, next to each other allows me to formalize that in a very strict way. But I can also model something that many people will view as socially maladaptive. I can, for instance, define maximum partisanship, maximum bias, if selection is only about group membership. So in the right example, you can see a mechanism where S equals G. So I've selected only the Greeks, then none of the Romans. But equality does not get us very far. What really gets this ball rolling is the concept of independence. And now it gets a bit harder. So this is where we will stay most of our time. We need this concept of independence from high school math. Just remember that 2 random variables independent if the conjunction factors as in the definition here. If you're not a math person, then just read independence as a very formal way of saying A has nothing to do with B, or A is not influenced by B, and it's a symmetric concept. So if A is not influenced by B, then B is not influenced by A. Another way, an information theoretic view of this symbol is that A contains no information about B. Think of, so a useful intuition is to have this as some kind of coin flips, random process. So, and with independence, I can introduce our first fairness notion, easily the most popular one, demographic parity. But this is a slightly overloaded slide. Let me walk you through this. In the middle of the slide, you see the three symbols, S independent of G. Read this as selection is independent of group membership. And the picture to the right shows you a prototypical example of it. You can see we selected 2/3 of the Greek population. We selected 2/3 of the Roman population. The selected population is not 50-50, but it reflects the demographic markup of the base population. There are twice as many Romans as Greeks in the population, and there are twice as many Romans as Greek in the selected population as well as in the unselected population. So this is easily the most widespread and most widely held fairness intuition. Let's call it demographic parity. In this talk, it has many, many names because there's a there's a rich literature about fairness in social choice theory, philosophy, mathematics, machine learning, statistics, and so on. So it goes by many names. Darlington's fourth fairness criterion, maybe even the poshest one. Independence is what it's sometimes called, or just group fairness, equal outcomes, or equity in many social theories. Many people have this as their only fairness criterion. In fact, this goes so far that if a violation of this fairness criterion is observed, then to many people, this indicates discrimination somewhere along the process. Demographic parity is simple because it's very easy to achieve. You can just introduce quotas. And it is good in the sense that equal representation feels fair to many people. The criticism, of course, currently is clear that the target value T does not even appear in the definition. So if you put value on utility, then this is then this framework does not allow you to talk about utility at all because T does not even appear. And let's just finish these ways of gluing variables left and right of the independent symbol. So here's target indifference, which means that selection is independent of target value. So this is the opposite of selection being equal to the target value. So here we are maximally indifferent about the utility of the outcome. And this is, again, an extremely well-studied concept in social choice theory. It's called sortition in voting theory. And there are many processes in many societies that use exactly this process. Jury selection is an important example. Military draft in many countries. Many elections use this mechanism for tie breaking. And since it is often implemented by some kind of random process, this is viewed as fair by many people. It has many positive aspects and, of course, also a lot of negative aspects because utility may actually feel important to you. So if you're in a context where utility is more important to you than, for instance, equal representation, then this is not a good fairness condition. And the third way of using independence in two variables is also comes by many names, equal base rates or absence of group differences. The catchiest name I found in the literature for this is we are all equal, so I will stick to that. So we are all equal is the fairness intuition that groups, that there are no differences in target base rates among groups. So graphically, you can see that on the right. You can see that 2/3 of the Roman population is in the target population and 2/3 of the Greek population is also in the target population. The two target populations are not equally large, but the presence or absence of target value is independent of your group membership. And this is, again, an extremely widespread fairness notion. It is underlying many social theories and even entire religions are built around this fairness notion. We can't really achieve this because S doesn't appear. So we here, engineers that try to improve the fairness of selection mechanisms, can't really don't have much to say about this because S doesn't even appear in the definition. Right. So to sum this up, we have these three fairness notions, demographic parity, we're all equal, and target indifference, all of which appear naturally from gluing these three variables left and right of the binary independence symbol. Let me just walk you through them again. Demographic parity is mainly a claim about the outcome. This is an outcome fairness notion that says that an outcome is fair if the selection is independent of group membership. The one in the middle, we are all equal, is more a claim about reality than it is a claim about the outcome of a selection process. And the one on the right is the knob you can twiddle with in order to explain how important utility is for you. So outcome, reality, and utility have different effects on, or represent different ideas of what fairness should be, and they're all here. So this ends the first half of what I call the fairness six-pack. This is the easy part of the fairness six-pack, and there's not a lot to say about this. So these three notions can all fail to hold. So there are three variables, and each of them can either be satisfied or not satisfied. So that gives you 8 different ways that these could combine. And just take it on my authority that all 8 of these make complete sense, and they can hold and they don't contradict each other. For instance, you could live in a world where all 3 of them hold. I tried to draw that at the bottom row of the matrix to the left. So all 3 of them could hold. Or the first row shows that all 3 of them could fail to hold. A particularly interesting one is the 5th one, where the first 2 hold and the last does not hold. So I can call that the egalitarian utopia. That is where equal outcomes are satisfied. So the outcome of the selection process is independent of group membership. In other words, the demographic parity holds, or there are equal group outcomes. Secondly, we live in this world where we are all equal, so there's no base rate difference in target value among groups. And thirdly, we managed to build a selector that is flawless, so S equals T. So S independent T fails maximally. So this is the desired goal state of many of the conversations that we have. We make a utopian claim about the world. We make a desired state about the quality, and we make 2 desired claims about the outcome of our selection, namely that it is flawless and achieves equal outcomes. And if there are no group differences, this is actually possible. This is not a mathematical impossibility. And you can look at all these 8 different combinations and find the ones that you like most or detest the most. It's not important. Right. This was the easy part. Now it gets hard. Pay attention. I will have a sip of coffee. Because independence only gets us so far. Everybody in the room, in the virtual room, that has ever taken a machine learning class or some kind of data science education will know what comes now, namely conditional expectation, conditional independence. So that's much harder to understand. So let me walk you through that. So A and B are conditionally independent given C. And there are at least 3 ways in the literature of writing that. So A and B are conditionally independent given a third variable C. And then you can read the definition if that kicks your boat. If you like definitions, then the same factoring property that traditional independence has should now hold once we condition on the third variable. If you've seen this before, it's a banality of the highest order. If you've never seen this before, this will be a lot to absorb. So instead, think of this intuitively as A and B are independent if only I knew whether or not C has happened. So C contains all the explanation for A and B being not independent. Let's see an example. Again, this is a famous example if you've seen this before. So the process is like this. 3 things happen. 1, Claire randomly picks one of 2 coins, coin 1 or coin 2. You can see the coins are very different. Coin 1 comes up tails with very high probability and heads with very low probability. Coin 2 comes up heads with very high probability and tails with very low probability. So the process is Claire randomly picks one of the 2 coins, gives that to Alice, who flips that coin, and then gives the same coin to Bob, who flips the same coin. Now, depending on how good your intuition about random processes, it should be clear that A and B are certainly not independent. If we observe the outcome tail from Alice, then there's a very high chance that we also will observe the outcome tail from Bob, because the best explanation for Alice's tail would be that Claire gave her coin 1. And conversely, if Alice comes up heads, then there's a good chance that Bob will do the same thing. He will also come up heads. So the coin flip of Alice and the coin flip of Bob are highly dependent. However, their entire dependence is because Claire made some random process first. So if I knew Claire's outcome, then A and B would again be independent. They are coin flips, they're not magical. Right? So this is the standard explanation of conditional independence. It's a quite natural concept, even though it looks somewhat scary. So intuitively, knowledge about whether C occurs makes A and B independent. They are not independent, but if C was given, then they become independent. Or an even niftier way of saying that is that the entire dependence between A and B is explained away by C. So that was the formal part, but I promised to do everything by drawings. So we'll get back to drawings and get back to the fourth of our fairness notions, equal odds. So the pithiest way to define equal odds is to say that S and G are independent given T. So that is the by now standard definition of equal odds, sometimes called separation, or that all the error rates are the same throughout the populations. So in other words, conditioned on the target value, demographic parity holds. And if you're still following this, then stare at the big picture in the middle. That's an example where equal odds hold. It's pretty hard to pass. So break this down into two, the dark and the light one. So the dark one, T equal 1, is actually pretty easy to understand, and T equal 0 is also pretty easy to understand. So let's look at T equal 1. That is the image in the right side of the slide, the top image on the right side of the slide. You can see there that exactly half of the green population was selected and exactly half of the red population was selected, even when I restrict to the target population. And the same is true for the untargeted population. You can see we selected 1/4 of the untalented Romans, and we also selected 1/4 of the untalented Greeks. So we made equally bad positive errors about both groups, and we made equally bad negative errors about both groups. So given that I restrict the population to T equal 1 or T equal 0, I actually did manage to achieve that S was independent of G. Given that these two restrictions, equal outcomes held. And this is called equal odds. Your odds should not be influenced by, your odds of selection should not be influenced by your group membership. No error type disproportionately affects any group. Again, this is a super well-known fairness notion, which goes by many, many names. And I can play around with these symbols in a fifth way, and then I get this. Target value and group membership are independent, so we are all equal, given that I restrict my attention to the selected or unselected groups. This is sometimes called sufficiency, or the Cleary model, or predictive rate parity. A good way to understand this and build some intuition is to think of this from the employer's point of view. We would like the graduate from some schools. If you graduated from Harvard, then the employer would like that diploma to be equally informative about your target value, no matter which group you belong to. Okay, and this is even harder to draw. I tried in the middle of the slide, and even I have difficulty understanding what exactly is drawn there. So at the bottom of the slide, I've taken a special case, which almost contains the entire story, but is somewhat easier to understand. So you can see at the bottom of the slide a situation where T is independent of G, so we are all equal, restricted to the selected subgroups. So at the bottom of the slide, I've drawn the same situation twice. I just moved the boxes around a bit, and the picture at the bottom of the slide to the right is the easiest one to understand. So if you restrict your attention to the framed subpart of that picture, then you can see that in that framed subpart, indeed, we are all equal because we have achieved this situation where both of the subpopulations, the green subpopulation and the red subpopulation, as you can see, exhibit the same frequency of talented individuals. The target groups are equally large in both subgroups in relation to the population sizes. It looks as if there's dark green and dark red fluid in this box, and that the level of fluid has the same height. That was exactly my first image for we are all equal. So this is predictive parity. We want the prediction to be independent of, we want the target, once the selection has been made, we want groups to exhibit the same base rates. The last two things I showed you, equal odds and predictive parity, play a big role in fairness studies. There was a very well-published example about recidivism scores. So that the selection mechanism was given the your proclivity to reoffend. So a criminal is determined to be a high or low risk for reoffending. That's called recidivism, and it was correctly observed that according to some of these fairness criteria, groups were treated unequally. So these are famous examples in real life and produced a lot of interesting papers. So just to finish this off, the 6 of my fairness notions are stratified in difference, where S is independent of T, so we don't care about the quality of the selection. We are target indifferent, but we do not treat both groups equally. And this may again clash with your intuition about what is fair and what is unfair, but it is a very widely used mechanism, for instance, in military draft. Many countries randomly select males and only males for military service. So you treat people randomly, but you also let the probability of being selected depend on your group membership. This is exactly this, stratified indifference. Okay, so this ends the part where I just defined concepts. So all of these 6 fairness notions are now defined, and in some kind of complete and symmetric way. There are no other ways of gluing these symbols around independence, the independence perpendicular symbol. So here are our 6 fairness notions. And the first question you might ask is, of course, how do the columns compare? For instance, demographic parity and equal odds look quite close, right? Both are a claim about independence of selection and group membership. One just conditions on this third variable. So does one imply the other, or does the other imply the first one? And unless you have extremely good intuition, this should be a real question. Right? So you may have seen these arguments before, in which case this entire presentation is going to bore you. If you've not seen these arguments before, this actually should give you pause. Does demographic parity imply equal odds? Or do equal odds imply demographic parity? Or neither, or both? And let's just get that out of the way, because I can draw these things. So the answer is no, they don't imply each other, not necessarily at least. And in the left side, you can see an example where equal odds holds, but demographic parity is violated. So look at that for just a moment. You can quickly see that demographic parity is violated. You can see that we are selecting twice as many Greeks as Romans, even though the Greek population is much smaller than the Roman one. So this is certainly not demographically equal. On the other hand, equal odds are achieved. That's not so super easy to see. You need to see that the error rates are the same, but they are. You can see that we are selecting 1/4 of the talented Greeks, and we are selecting 1/4 of the talented Romans. So the the true positives, no, the false negatives have equal size, and we're not making any mistakes. So the negative errors are also equally absent in both populations. So equal odds is certainly achieved, and demographic parity is certainly violated. So one does not imply the other. And the other picture shows you the contrapositive of that you can have a situation where demographic parity is achieved, as in the example to the right, but where equal odds are violated. You can see that we do treat the talented Greek population worse than we treat the talented Roman population, of which we take everybody to achieve demographic parity. Okay, so the notions here are don't imply each other, so we need all 6 of them. And 3 of them are close to people's fairness intuition. Right? This is not a symmetric picture in the sense that the dark shaded fairness intuitions are something that we would like to do something about. We can we seem to be able to influence them by making choices about our selection mechanism, whereas the other ones are claims about the world or claims about utility. So the three interesting fairness notions from an engineering perspective are the three that I highlighted here. And one does not imply the other, so you can choose maybe one or two or three. So and then it's a real choice, and many values are built into that choice, which of these fairness notions you would prefer. So let's first try to just achieve an entire column. So let's try to achieve both equal odds and equal outcomes. I claim just anecdotically that this seems to be the most widely held naive intuition about what fairness should be. We should have equal odds and we should have equal outcomes. So we already saw that they don't imply each other. So they also don't contradict each other. So here's an example where I have achieved demographic parity and I have achieved equal odds. And it's maybe a slightly simple example because I also assume that we are all equal. So in a situation where we are all equal, so target and group membership are independent of each other, I can indeed satisfy both equal odds and demographic parity, and the pictures down there below. You can check that all the error rates are the same, and clearly the populations have been sampled in proportion to their base presence. And there's another example, another simple example here. If I'm indifferent about the target, then I can just flip coins, for instance. So one simple way of implementing it is just to flipping coins. And if I flip coins, I get the picture below, in which case demographic parity holds just by virtue of the coin flip being fair, and equal odds also hold by virtue of the errors being equally distributed because they're just coin flips. So there are plenty of examples where demographic parity can hold and equal odds can hold. Both of the examples here were maybe a bit depressing because they assumed either an unrealistic claim about the world, maybe that we're all equal, or they rejected utility out of hand because we assumed target indifference. And now, and this may be expected by some of you, the depressing observation is now, of course, that these are the only ways of achieving both equal odds and demographic parity. Slight footnote here, if I could ask the technicians to give me my slide back, because I can't see my slides right now. I see one of the attendants, but I would really like to see my slides while I talk over them. Yeah, hi. Nice to see you, whoever you are, but I would prefer to see my slides. Because this slide is important because it breaks many people's hearts. If demographic parity holds and equal odds holds, then there are only two different ways that the other variables can behave. Either the base rates are the same, so we are all equal, or utility has no value for us. We are target indifferent. And this is a matter of discrete probability of the highest banality. It's half a page of just moving symbols around. It's really, really simple algebra. And if this was a technical talk, I would now spend 5 minutes walking you through the proof. But just take it at face value. This is really, really easy to prove. So demographic, assuming both of these fairness notions at the same time trivializes the problem, because it takes away everything that makes the problem interesting in the first place, namely that people typically are not equal, groups are not equal, and indeed we do care about utility of selection. Okay, and I can play this game with all other ways of choosing two of these. So for instance, if I choose demographic parity and predictive parity, another, I think, this is actually closest to my own personal intuition about what a fair selection process should be. If I assume these two, then I have also implicitly assumed that we are all equal. So the only way that demographic parity and predictive parity can hold is if target value and group value are independent. And there's only one way I have not checked yet, namely what happens if two of the conditional independence notions hold at the same time. Well, if two of these hold, then both of the notions at the top also have to hold. That's slightly more involved probability, but it's still very simple. Okay, so if you assume equal odds and predictive parity, then you have implicitly assumed demographic parity and we are all equal. Okay, so there we go. The upshot of all of this is here are 6 very clean ways of defining fairness using very, very little math. You can have any combination of the fairness notions at the top They can all fail to hold. They can all hold. Two of them can hold. As soon as you add one of the fairness notions from the bottom, then you are in the situation that you can pick exactly one of those. You can't even pick two of these fairness notions without trivializing the entire problem to a situation where groups are groups by name only. Right. So let's get to the summary. Unsurprisingly, this is a complicated topic, and as soon as you try to write things down, then your moral intuitions desert you and will not help you navigate this at all. On the other hand, outrage is super duper easy. You can build a system that perfectly satisfies one of these fairness notions, maybe the one that was your job to satisfy, and then you can maximally unsatisfy one of the other fairness notions. So even when you try to build a system that is fair, according to one definition, you are guaranteed to have built a system that has measurable unfairness in one of the other notions. So outrage will always be there, and outrage can be a perfectly good source of energy for political activism or social change. So maybe this is a good thing. I'm almost comically agnostic about this. The fact that various socially adaptive ideas of what should be fair are in conflict with each other should again be no surprise. Everybody who studied social choice theory or just statistics knows that results like this are everywhere. As soon as you write down 3 desirable properties of a voting system, you will have reached a contradiction. And yeah, statistics is full of these ideas. So again, the fact, heartbreaking as it may be, that writing down and being precise about fairness intuitions puts you in a situation of inconsistency is depressing, but the expected result. So, but just to say everything I said very pithily, if you want a group-based fairness notion and you try to formalize your intuition about that group-based fairness notion, then these notions necessarily contradict each other unless you're in a situation where you don't care about quality of selection, or you're in a situation where groups have equal base rates. This was a super brief, hopefully more or less consistent introduction to this topic. There are dozens of group fairness definitions in the literature. I know and understand most of them. My ambition here was to restrict the attention to only 6 of them in a more or less symmetric and natural fashion that still allows many of these phenomena to be discussed and actually proved. So there's a whole jungle out there. I encourage you to look into that. Much of what I'm showing you here is based on this clever idea of viewing independence as explained by other phenomena. And there's a famous book by Pearl that many of you know, of course, called Causality, which would be a good stepping stone to explore this further. And there's also now a nice book by Hart and others, which you can look up. It's free, which contains many of these things with lots of real-life examples. I didn't even touch on the other discrepancy between individual and group fairness. So I tried to restrict my attention only to what happens when you look at group fairness. Of course, notions of group fairness also contradict notions of individual fairness. And that's a whole other can of worms that I have not even opened. I just want to point to it. As a fifth thing, maybe for discussion, there's by now a very strong research agenda behind all of this. There are conferences devoted to it. A lot of the discourse is defined or informed by notions from the United States about what fairness is. And in 1964, the Civil Rights Act, the United States seems to have taken sides on which of these perfectly symmetric fairness notions is more important. The United States has a lot of focus on equal outcomes, or demographic parity. That goes so far as it is enshrined in the law, at least a weak version of this. And there's a lot of really good work done on this by American researchers. What I'm not sure about, and this is a genuine question, is whether European fairness notions necessarily align with the US understanding of fairness, and whether there would be room for establishing a separate European research agenda that maybe focuses more, for instance, on equal odds than on equal outcomes. And this is a genuine question. I don't know the answer to it. This ends my talk. Thank you very much for your attention, and I give the word back to our moderator.
Thank you, Thore. Very nice talk, actually. I mean, I love to see your attempt to quantify these issues in terms of like these statistical terms of independence and conditional dependence. So we have achieved a lot of questions from the audience, so I will start with it, but I will actually sneak in my first question first, since that is my privilege. So to get adoption in the community with tools like this or frameworks like this, it's often very useful to actually make a Python package of it that people could just put in their code and see how fair was my algorithm. Have you thought about actually doing something like that?
So to some extent, this exists, right? There are several Python packages that already do this, and R packages that, and I have, some of them are quite open about which fairness notion they actually support, and others seem to assume that this is just understood. At this place, this is a very ripe opportunity for a nice bachelor thesis and master thesis to explore this.
Okay. Yeah, I'm sure there are many listeners out there that are in that position, so maybe they can apply to you for that.
I'm fully booked, but yeah.
Okay. So yeah, please add the links to these Python packages somewhere, or we send them to us organizers, so we will put them in Slack or in the YouTube.
Okay, that's a good idea.
Like
Yes, I should do that.
Thank you.
I am trying actually to write some kind of survey up on this because it doesn't take many pages to really do this very carefully and dot all the I's and slash all the T's. And of course, that should naturally have these references that you bring up. Yeah.
Okay,
as soon as I fall into a black hole of too much time, I will write this up.
Okay, great. So let's go with the first audience question. And that's Denise. He's or she's asking, in some fields, do you see before you that there will be some third party, some organization that will apply these algorithms as a standardized test process in models that are applied out there?
I would even assume there will be some kind of seal of approval that you can stamp on your decision procedure. So just like we are certifying CO2 emissions, I assume that there seems to be a real desire from industry to have some kind of stamp, an ethics stamp in your face that says that your mechanism is fair in the following sense, blah blah blah. So, and this can be both good and bad. I think currently there's very low-hanging fruit, which will just lead to ethics washing, some kind of performative claim about the fairness of a procedure based on a highly selective set of parameters. As you mentioned in your introduction, there will be plenty of talks after this, there are a ton of different sources for bias. Just in data collection, for instance, sampling, or just defining what S should mean, and so on. And I think if you want a source of bias to remain there, it would just find the empty hole to sneak into, and then it would remain there. But I fully expect there to be strong pressure in industry to find mechanisms that do certify fairness in some way. And what I think we as a research community should be pretty careful about is that these make sense, rather than just being an empty label put on terrible decision-making procedures.
Okay, so we as a community can maybe take the first step now to start applying these methods to algorithms in a sensible way to actually try to put a stamp on it. So I think we have time for one more question. Johan asks, what is the best way to apply fairness in practice? Do you see, like, how should we start when we go back to our workplace on Monday?
So that's a value-laden question, of course, and deciding between these fairness notions immediately aligns you with well-established social theories that have strong, sometimes century-long traditions of ethics behind them. I don't like using a platform like this to tell you what I think. I would not want to explore my authority to. So, Johan, whoever you are, if we ever meet over a beer, I'm happy to tell you what I think. As an algorithms person, an AI person, I very much like the transparency idea. So I think notions of transparency of the process to actually see what's going on by exposing as much as we can of the procedure. I think these are good old-fashioned computer science values that we just need to adhere to. And then as soon as the mechanism becomes legible, lesbar, so as soon as we can understand and describe the mechanism because it has been exposed to us, for instance, by the program being short and readable and understandable, then that mechanism can be subject to criticism, just as laws normally are. And I think that's the way the open society should tackle this.
Cool, thank you. So that was the questions that we had time for. So thank you so much for your very interesting talk, Thore, and hope we hear more from that area in the future.